Instantaneous velocity is defined in 3 dimensions as the derivative of the position vector with respect to time. In Cartesian coordinates, this velocity has 3 components: Vx, Vy, and Vz. Thus, we need to find the magnitude and direction of this velocity vector. In its simpler form, in 1 dimension, the velocity has the derivative of position x with respect to time, which gives the magnitude of the velocity vector in 1 dimension. However, as long as the motion is along the x-axis, the direction of the car in our demonstration is due to east. The car, as it has a speedometer, and this speedometer reads the speed as 120 kilometers per hour. This speed represents the magnitude of the velocity. The car continues its motion towards east, but the magnitude of velocity is reduced to 100 kilometers per hour. The car runs out of petrol and the driver decided to stop near a gas station, so the speed of the car reads 0. The car continues its motion towards east with a speed of 160 kilometers per hour. The car has different instantaneous velocity during its trip, as the speed changes from 120 to 100 to 0 and then 160, and this kind of motion is non-uniform motion. The non-uniform motion can be demonstrated by showing the race car at different locations and different times, having different velocities. As we can see that at 30 meters from the origin, at time t equals 0, it has a velocity va, and then this changes to another velocity at a location of 50 meters with time 10 seconds, and then change its direction towards the west with a distance for almost 40 meters from the origin, and so on. So again, this is another example that demonstrates the change in velocities of an object. The position of the race car, as measured in meters, is plotted versus time in seconds in this curve. So the different locations A, B, C, etc., represents, of course, the positions of the car at different times. And here, what we are going to do, we want to find the instantaneous velocity at each location, at each position. So to do that, let us start with point or position A. On this curve, we can draw a straight line tangent to the curve at point A. Doing that, each straight line has a slope, and the slope, finding the slope, means finding the velocity at point, the instantaneous velocity at point A. How can we find the velocity at point A? Again, we need to find the slope. To find the slope, you have to have delta x and delta t. To get delta t and or t initial and t final and the corresponding position x initial and x final, we start, for example, from here. We draw this line up here to t0. We know this is the initial time t0. This initial time we have a corresponding x initial, that is the x initial. And also from here, from any point on this straight line like this, we also draw down going down to time t final. And this t final has a corresponding position x and here x final. So now we have here x final and we got here x initial, and x final and x initial have their corresponding times. So the difference between x initial final and initial give us delta x, and also the difference between the time final and time initial obtained from the graph give us delta t. Divide delta x over delta t, you're going to get the velocity. The velocity in this case, as the slope says, might have a positive value or a negative value. Obviously the results here give us a positive value as x final is larger than x initial. This means, and we're going to get a large value or large magnitude for the velocity. This means that the velocity is greater than 0, which indicates that its motion towards the east, as the positive sign indicates. Here we're going to find the instantaneous velocity at point B. Again, following the same procedure as before in A, we're going to draw a line tangent to the red curve again at point B, and then we'll determine the slope of this straight line. The slope of this straight line will have also delta t and the corresponding delta x. Delta t and the corresponding delta x. Obviously, delta x over delta t will give us a positive value, but here the magnitude is less than the one before. And the positive value indicates again that the car is still moving towards east. Now, repeating the same method in finding the slope at point C. So we draw that line tangent to the curve at point C, where this line will have an initial time and a final time, t. The initial time will have a value of x. It's a bit large, while the final time will have an x less than the initial one. Obviously, we're going to divide delta x over delta t as before, but delta x in this case is going to be negative because the final position is less than the initial position. So in such case, the slope of the straight line turns out to be negative value. It has also a good magnitude of the slope. So in here, Vx is less than 0, and the negative sign indicates that the car is due west. Repeating the same method as before for the location D, and then drawing a slope, and the slope here is still negative, the same as that in C, which indicates that the car is still moving towards west. However, the magnitude of the slope looks larger than before because this slope is steeper than C. Thus, again, the velocity here less than 0 indicates that it is moving towards the west, and it has a larger magnitude than that in C. Do the same procedure at point A, E, and draw the slope, and the slope here looks shallower than the one before, which means that the magnitude of the slope, which indicates the magnitude of the velocity, is less than that in D, but it still has that negative value, which indicates that the direction of the car is still on due west. Again, for point F, draw a line tangent to the curve at point F, and then find the slope. And here you're going to get the slope has a negative value and a magnitude less than the one before. Yeah, we learned from this session how to find the instantaneous velocity from a graph.